welcome. I'm live streaming this one, so it's going to be a few seconds of just making sure the live stream is working fine before I get into it. So this question is an interesting one. This is about the
Making
spiral
sure the live
matrix
stream is
4
working
fine before I get into it. And it looks like the stream is fine. Very interesting question. We'll discuss it. So last time I was working on problems, I didn't complete it. I actually got stuck, and I had to take a break and come back to it. So let's read the question, and then I'll talk about some of the ideas, some of the solutions involved that are, I think, quite good. So it's 23, 26 spiral matrix 4. Solve this one. They were given two integers m and n. You know, actually, there's something I want to change. What did we say it was 23, 26? Hold on. So the given two integers m and n represent the dimensions of a matrix. Okay, so the basic idea here is I'm going to be basically plugging in elements into a matrix in a spiral pattern into an m by n matrix. And it says you're also given the head of a linked list of integers, generate an m by n matrix that contains the integers in the linked list, presented in spiral clockwise order, starting from the top left of the matrix. If there are remaining empty spaces, fill them with a -1. Return the generated matrix. And they give some examples. So I kind of got stuck on this. It's got a very high acceptance rate. This is one of the easier questions, but I struggled with it a bit. And the reason is that I kind of didn't think it all the way through. So my solution previously was I was thinking about using a, oh, what happened here? Oh, there we go. Okay. I was thinking about using a like, I guess a more complex approach that was sort of each leg of the spiral, and I was trying to, I guess, calculate how far I should go on each leg. And it's not really necessary to do that. So an easier way to do this is more like the following. So this is actually the solution I ended up going with. I'll code it again from scratch, I think. So I have a result, and then I've got fill with -1s. And then the way this is going to work is I have this list node current, starts off at the head, and I'm going to have this for loop. And basically, while current has a value, I'm going to update current next. And I'm also going to have a few different integers here. I'm going to have a drd and dc, which is the change in the row and column at each step. And then I'm also going to have a row and column, sub row and column values. And the idea is I'm going to have this const bool check. So first things first, I'm going to write at R and C the value of current. And then I'm going to update this this new row and column with, I'm going to add the change in the row and the change in the column. Actually, the first change in row, change in column, we're going to start by going to the right. I'm going to write this check. We're going to perform this check, and the check is going to do a couple of things. So there are at least two ways to handle this. So one way is check if we're out of bounds. So new row is less than 0, or new row is greater than or equal to m, or new column is less than 0, or new column is greater than or equal to n, or the result of new row and new column is not equal to -1. So meaning we've already written. So either we're out of bounds or we've already written to that spot. If the check fails, or if the check succeeds, so if we found that let's say overextended is maybe better, or boundary reached might be more appropriate. So if we've reached the boundary, then we're going to change directions and recalculate the new row and the new column. We're going to update the row and column to the new row and new column. And these shouldn't be const, actually. And the way we do this is we're going to, now, in order to update the direction and the new position with that new direction, what we're going to do is we're just going to rotate the direction vector, which is going to be in 2 dimensions. It's going to be the DRDC. So right now it's moving to the right. We just rotate it 90 degrees each iteration. And as it turns out, instead of using, like, one way of doing this is to have an array of directions and just switch through the directions, loop through the directions. As it turns out, that 90-degree rotation is very straightforward to compute, and all you've got to do is just multiply, the change in the row direction by -1, or the row direction by -1, and swap that with the column direction, and this will appropriately switch between each direction as desired. And so you don't even need to have like a more complex logic for picking the new direction. And then you just recompute new row and new column. I think it's that simple. Yeah, so if you start with 0, 1, then negate 0 is still 0, swap, you end up with 1, 0, which is correct, going down. Then from 1, 0, negate, you end up with -1, swap, you have 0, -1, they're going backwards to the left. Then again, negate 0 and swap, and -1, 0, you're going back up. And then negate -1, swap, you end up with 0, 1. So you can easily check that this approach gives you the right directions. And then I think that's all is required, basically. That's all that's required. You just write in, using this very clever approach of what it's going to do is it's going to write the new value where you're at, check the next value, whether or not you can reach it. If you can, we're going to go there. If not, we're going to switch directions and go that way. And it's a very simple approach. Very clean, and yeah, works nicely. Beats, does pretty well. May not be the most efficient, but it's reasonable. And so this is the solution that I came up with after kind of pondering the question again a little bit longer. It's not the most efficient. It's also, interestingly, you could do it a little bit of a different way, and instead of using this value, checking the boundary could actually you could actually just have multiple bounds. So we have int left bound 0, right bound, so we'll just say b, lb, rb. So left bound is 0, right bound is m, upper bound is 0, and lower bound, say left bound, lower bound, upper bound, lower bound, is n. Oh no, excuse me, actually lower bound is m, upper bound is 0, right bound is n. And instead of using this approach, one could simply say NR is less than left bound, or NR is greater than or equal to upper bound, or right bound, or NC, it's not the left bound, that's actually the lower bound and upper bound. On the other side, and actually this is the lower bound. That's getting a little bit confusing. And the column being less than the left bound or greater than or equal to the right bound. And then when a boundary is reached, updating the boundary. So in this case, it might be easier to depends on which case it was. So we'll do B1, B2, B3. Yeah, this I was thinking about a little bit more. And I want to identify which one. Actually, this could just be. And we're going to update the boundaries. So if we reached so it could be UB, lower bound, left bound, or right bound. And the idea would be if our row is lower than the lower bound, so that's B1. Actually, yeah, let's do B1. So let's do each one. So B1 is the upper bound. If we're found to have exceeded the upper bound, that means that we're going to move to the right, and that also means that we've got to actually add B1 to it's actually the left bound. The left bound gets +1 from B1. And if we exceed on the right side, we exceed the right bound, which means NC is greater than or equal to RB. That actually means we've added a layer up top. That means the lower bound for the number of row lower bound. Or excuse me, actually this might be wrong too. Oh yeah, lower bound is a little bit confusing because it's actually at the bottom. Or let's say last row is probably better than lower bound. Last row. And then upper bound is like first row. This is probably more appropriate. Let's do last column, first column. These are much better, I think, words, phrases. So the new row is less than first row. New row is greater than or equal to the last row. First column, last column. Yeah, this makes a lot more sense. I do it this way. So now if we, I know these will be first row, last row. Yeah, that's much better. That's a lot easier to think about. Okay. So now when does the first row get updated? Get a +1. That's on the first iteration when we've exceeded the right boundary, which is the last column. So that's on B4. So we increment on B4. When we update the last row, that's actually on the next, that's actually on after I finish the last row, which is going to be when we exceed the first column, which I think is B1. No, it's B3. So yeah, once I've exceeded the first column, that means I've got to increment the last row, and actually it's a decrement in this case. So decrement the last row, increment the first row, decrement the last row. And then the other ones are B1 and B2. And first column is going to be, I'm going to add another column, increment the first column over. So first column increments. And the first column increments when I've exceeded the first row, B1. Yeah, something like this also works, I think. And this is more of like a counting approach, which doesn't access the array repeatedly. Yeah, and this seems to work. I'm going to submit this one and see if it works. And this one's correct too. So that was the other idea that I had. There were two ideas that I had. One of them was to check if I already wrote into the matrix using the sentinel values in the matrix. And if I've already written to it, then a lot of this logic can be obviated because I could just check that directly and keep it simple. But if not, if I don't have, if it's either it's more advantageous to do it this way, or I don't have that sentinel value available to me, or for some reason, this is another approach that instead of counting directly how far I need to go, how far I need to go on each leg of the spiral, I can just set the bounds of the spiral and update that on each direction change. Each direction change basically completes another leg, and that updates the bounds on the spiral as I go. And I think that's a much cleaner way. And these could be renamed to like breached first row and breached last row instead of B1 and B2. So B1 is breached first row. B2 could be breached last row. And then B3, B4 be breached first column. And then this could be breached last column. Yeah, and I think this is still correct. So when I decrement the last row, that's when the first column is breached. Yeah, that's correct. I think this is the right kind of this is sort of the right and all the different values. Okay, something like this. This is, I think, semantically a lot easier to understand, to grasp what's going on, and then the relationship here needs to be, the correct relationships need to be encoded here. I think this is a very clean approach. Overall, very clean and not too hard to understand, pretty straightforward to understand. Is it fast to program? A little bit. I mean, the breaching portion is not as easy to program or obvious because you've got to encode those relationships, but it's not too hard to understand. You can do it fairly quickly. A little bit of preemptive, a little bit of practice beforehand. This isn't too hard. Getting the naming right on these variables, though, is probably important, so it's easy to understand what's going on here. So yeah, I thought this was a good question and pretty interesting to go through the solution that I came up with. There were two variants, like I said. There were actually a few different things that varied here, but there's yet one more way to do this that's clever, and it would be basically this breaching logic. Instead of doing a swap with these variables and recomputing, it's not as good, I think, to do it that way, but you could do each leg one at a time, one after another, until there's a breach, and then you do the swap. So what could be done instead is something more like the following. There's another way to do this that's kind of interesting, and it would be basically have this for loop where you would say so it's going to be r plus dr is, so this one would be, if we're going to the right, it's going to be, we don't need dr dc anymore. We're going to do it this way. It's like another approach. So the right side would be, or the row, we're going to increment the column. So the column is going to be less than the last column, or increment C. We say result, and we also so we have current and we also update current. And we say result of RC equals current value. And we would keep incrementing C, and really it would be C plus 1, right? It's less than this last column. Yeah. So there's a look ahead. So the position, we're in the right spot. We do a look ahead. If the look ahead is out of bounds now, then what we're going to do is we're going to update the, in this case, it's the first row gets incremented. So I mentioned that before, right? So now we update the bound for the first row. Now it comes down, and we switch directions now. And what we're going to do now is C plus 1 is outside the boundary, but C is not. And now we just switch directions to go down. So now going down, we're going to say R plus 1. Increment R. And this is going to be last row. Almost the same logic. And then now we decrement the last column. Right after this one's done, we've moved down, we decrement that last column. And then we do a similar kind of routine with the, again, the column minus 1. So column has to be greater than first column, or column minus 1 is greater than or equal to the first column. The way that I've defined the last row and last column also as not inclusive, which is maybe a little bit awkward. I could do it and make these inclusive, and then that may actually make a little more sense if I do it that way. And in this case, we're subtracting on C at each step. And then here we would say the last row is decremented. We do a similar thing again now. Column -1 is greater than or equal to the first row, or first or R -1 greater than or equal to the first row. Subtract, and then here we would say we increment the first column. So something like this avoids all of this extra logic, the swapping logic and the updates and all of that. This is just going to do each leg one after another, and if we run out of values, it'll just skip right through everything and exit. Something like this should work too. I was thinking about this too. I was like, is this simpler? Is this easier? It might be. I'm not sure if this is correct, but we'll find out in a moment. Yeah, this is correct. So this was kind of, oh no, Atili, excuse me, it's not. No, that's my mistake. Whoops. I thought it was correct. Not correct. Okay. Interesting. Right. One issue here is that's actually a good point. This one doesn't work correctly for some reason on. Oh yeah, it's gonna just keep switching directions repeatedly in this case in TLE. That's kind of subtle. I want to say. Yeah, so there is a logical error here, which I kind of keep missing it, but the last one, the idea was that it'll write to the position immediately, and then it's going to decide which direction to go, and then go in that direction. Yeah. Whereas here, they don't write immediately, and that's kind of where it gets a little bit awkward. It assumes we're going in a certain direction, and it has the exit condition before writing. And the issue there is, let me actually do it this way. Let me do it this way. We'll do int nc equals c. nc is less than or equal to the last column. Increment nc. And then write this new column. Let me try something like this. So if I do it this way, NC's in the right position. Once we breach here, I should actually go to the next direction, next position. So I should actually update R, increment the row, and really decrement the column, I think. I think maybe I don't use NC. I just do it like so. Just use some extra logic to kind of handle the turn. Maybe that's easier. Same thing, R, increment R, And when I turn again, so row is going to be one, it's going to be too far. And I've got to decrement the column, come back, basically perform one iteration of the next loop here. Maybe that's the way to handle this. This isn't too clean though. I don't really like the solution that much. Yeah. Excuse me. And then similarly over here, we would have to increment C to undo that last iteration, and then also decrement the row to come back up. And then here, increment the row to come back down, and then move to the right by incrementing C. So yeah, maybe not the best approach. I was kind of working on this before. I was working on something like this before, and I kept getting stuck. Like I had to think harder about this. Okay, now it's correct. All right. This is substantially slower, it seems. I thought maybe this would be faster because it uses less, I guess I guess it's sort of simpler logic in some sense. I'm not sure if this is better or simpler. Doing well. What's up, Yash? Hope your day's going well. Welcome. Howdy. Yeah, I'm doing okay, man. Doing okay. I'm working through this question to see of looking at the different possible ways to solve this, different ideas. Okay, so this did give me almost 100% speed. But I do think this is a slower solution. I think this is not as good as the other one. But my thinking is that maybe this is a little bit simpler, which it's not that much simpler, quite frankly. I think maybe a do while will be better in these for loops instead. But yeah, this logic is a little more involved, maybe not the best. I don't think it's as good as the previous one that I had. The previous one I think I had was a little bit better. Let me look at that one. But this works. This idea works. Let's go all the way back. I'm not sure which one's easier, which one's simpler. Gotta go pretty far back here, huh? Okay. Let's try this now. TLE. Oops. I may have either gone too far back or not gone far back enough. Also, how are you doing there, Yash? I didn't ask you how you're doing. I probably should have asked. This actually appears to be a little bit faster, this approach. Is it simpler? I think it's a little bit simpler too. Yeah, I actually think this is better. I think this is a better approach. I'm not sure. Also, these probably should be just less than or equals all the way across the board. Or greater than values. Yeah, I think this logic is just simpler. It just doesn't have all the extra loops in there, and doesn't have all the extra off by one kind of corrections. Basically just checks, figures out which side was breached. This probably should be boundary breached. It's probably breached. And then performs the rotation on the position, and then also updates the boundary values. I think this is probably the best. The other one, there is a simpler way to do it. I think I've expressed that before. If I don't want to use these kind of breaching limits, and that would be just to check or the result of new row, new column is not equal to -1. And I don't think and then I don't need to change the first row, last row values. Yeah, this is even simpler. This is probably the best, actually. This is probably the best approach because it's so simple and so easy to program and so quick. So easy to understand and it's fast. And yeah, I can remove all of this extra code here, these extra variables. Yeah, this just becomes I think that's right. Yeah. And then I don't need any of this. I think this is the best. This is pretty straightforward. Those other two approaches that I described, those are better for like if I don't have a sentinel value inside. If I don't have a sentinel value inside available to me for the checks, then those are better. But yeah, this is very straightforward code, very simple. I like this. I think this is going to be it. Okay, I'm going to probably, that covers most of the ideas involved. So I kind of explained like the swap and I explained like the check ahead and then decide which direction to go to and then just writing immediately and then deciding where to go. I think I kind of explained these things, all the kind of elements this that are quite good. I could also ask the AI about this too. See what the AI thinks. Hmm. Okay. Any optimizations and improvements? Let's see. Recommend. Let's see if there's anything that I missed because I'm not getting like 100% each time. Direction array, logic. Before computing next position to avoid unnecessary boundary checks at the last assignment. Both of those aren't really good optimizations I should make. Boundary variables. It says boundary variables are a little bit better, slightly. Oops, that's not what I wanted. So I had that before, the boundary variables. Slightly faster. Compute next position only once per iteration instead of twice. Once in condition, once after turn. Hmm. I don't think so. I don't think that's right. Yeah, I don't think that really improves this very much. Can't memorize a perfect solution. You build something and then you break it, improve it, break it again, improve further. What is your take on this? Yeah, I mean, you can memorize solutions. You can. There are solutions that can be memorized. It's just the problem with memorizing solutions is that there are too many solutions to memorize. So this is kind of like the reason why AI works, the ones that we have now are much better than the ones that were like what they called expert systems, where like they would basically you get an input and get an output, like a hash map of inputs and outputs. The reason why the AI systems we have now are a lot better, even though they have their flaws, is that they do a probability distribution on answers. Like they do a probabilistic kind of a approach to answering questions. And the reason this is so much better is that like if you had, let's say you had 100 variables and every variable could have two different values, storing the answer, like the inputs and the outputs, storing the outputs for all those different variables, if it's just a one-to-one input output, it would be 2 to the 100th different outputs, which is an extremely large amount of outputs. It's too much. Like it's too much data to keep track of. Too many answers to memorize, basically. But if you use a probabilistic model and you just each variable has some kind of probabilistic function that is an input into, now you can answer all of those 2 to the 100th different possible questions efficiently because your model is not it's not memorizing every single possible outcome. It's just memorizing a way to generate that outcome using a probability curve. So that's sort of how the brain works. That's kind of how human beings operate. That's how modern AI works too. It's probabilistic. It's not so in other words, memorization is not really probable. It's not exactly probabilistic. It's much more like trying to save that specific thing in specific pattern, specific sequence for later. But as I mentioned, like complex things have too many patterns to memorize, like very specific, highly specific patterns. So memorization works, but you need typically you need something more along the lines of like memorizing generalizable principles and then combining those principles to get a solution, because the number of possible questions you could be asked and the number of possible answers is way too broad. There are way too many to memorize everything. That's kind of the basic idea. All right, let's look at one of the faster solutions to see if we can come up with like something that's faster than what I had. Okay, so it looks like the fastest solution actually did do what I was doing before, where it did each row one at a time. Yeah. Huh. So I had something like that before. Let me look at my hold on, let's go back this way. Let's go to my submissions. Okay. Was this the one? No. Let's go back a little bit. Oh, not that one. Somewhere around here. Hmm. Yeah, it's this one. This was fast. It's fair. It was fast. Let's try this again. So this is the one that does one leg at a time. Yeah. Interesting. Yeah. Yeah. Yeah, you can memorize things. It's just there's only so much that's worth memorizing because it doesn't generalize very well. And so then you want to memorize like more generalizable principles and patterns. And I think that's kind of what I was saying about like ad hoc questions versus like knowledge-based questions. The knowledge-based questions are basically you can memorize like patterns that generalize really well to different problem sets and memorize them pretty easily. So it's like a lot of different algorithms that are applicable. But then there are more ad hoc. Look at this question is more like an ad hoc question. Then there are more ad hoc questions which require memorizing more niche things that more niche things, smaller things that don't generalize to like a lot more problems. So like spiral logic, knowing about spiral logic is like only really applies to spiral based questions, and there really aren't that many of those. So like you can memorize these things, but it's not really like good to memorize these things because they only apply to a very small number of problems. But as you can see, like there are quite a few different tips and tricks and techniques that I employed in these different solutions that are, like I said, they're pretty niche, pretty small. Like there's only a small number of problems that these could be like applicable to. But those problems do exist, and like the more experience you get solving problems, the more you pick up these kind of more ad hoc, smaller sets of things, smaller things to memorize. But yeah, it's kind of a blend of things that are generalizable and things that are highly specific. I'm just reading what this says. So this is this is suggesting this is like a much better solution. Performance, faster readability, slightly complex but standard. Cache efficiency is higher. Space. Boundary tracking is preferred. Okay. Updated code. I think this is probably the best, actually. The best solution is this one. This is kind of what I was thinking about doing the other day, but I kind of couldn't get the logic quite right. But yeah, this is probably one of the better solutions. Critical bugs. Okay. May reprocess already filled cells. Thatgirlcoder.com. Before last two loops. No, it's not necessary. The loops themselves. Track the bounds. Bounds are breached. Loops will just exit. No, it's not correct. Once the RC no, no. Now the AI is like hallucinating, I guess. Hey, are you in your vehicular mobile? What's up, Karim Vona? I may be in a vehicle. Maybe. Stationary vehicle. How's it going? How is it going? Let's see. Aren't required in this case. Specific implementation loop condition ensures no writes occur in the list ends. With built-in bounds checks. After updating the boundaries, dimension collapses the scarf, so it won't execute. Yeah, there we go. Yeah, actually, this case probably handles the generalist boundaries. Approach to. Yeah, it's probably also handles the generalist case as well. Yeah, it just doesn't quite understand it. Okay. So I've said this before about AI that like it's actually kind of a liability. Um, like when you try to use AI agents. Now, granted, this one's not as smart as the other ones are, I think. But if you use AI agents, you basically have like incorrect logic being baked in all over your code, and you have to like go root out all the wrong assumptions and the wrong thinking. Like I just did here. Like I had to sit here and argue with the AI. I was looking for some performance improvements, but I didn't get any. This is actually very close to the optimal. The 11 milliseconds was 100%. So this, I think if I keep running this over and over, I'll eventually get the 100%. Although there's more variability in the solution, which is kind of interesting. But yeah. Okay, so summarizing the spiral matrix approach, we've got each leg basically is handled separately, and then there's a basically when the boundary is breached. So I write immediately, and then I try to check, and then I move to the next position. And if the boundary's breached, then I change directions and I move to that next position, like sort of almost preemptively. So these may be better written as like do while loops, but this works okay. So that's the basic idea, basic premise. And then also it updates the boundary positions, boundary values as I go. So this I think is like one of the fastest and cleanest implementations. And it's reasonable to program it quickly. So cool. Let me see how are we doing on time? All right. I spent like an hour on this. I spent kind of a lot of time. So thank you all for watching. I think that'll be it for this question. But yeah, I just thought this is a really interesting question. I just wanted to go through the different ideas that I had for ways to program this. I also kind of got stuck on it the other day where I tried programming it and I tried a few things. I tried to do it really quickly and it was kind of just wrong. There were a few things that I did incorrectly. Whereas this is much cleaner. It's correct. It almost beats the fastest solution. It's very close. Yeah, this is a much better way of doing it, I think. And like I said, I went through some of the other solutions, the other like variations that could work. Interestingly, I think the other variations were a little more consistent with the runtime, though. This one, for some reason, the runtime is sometimes very fast, but sometimes much slower. I was trying to get an idea of like how I could do this more quickly. I'm wondering if dumping the. Let me ask. If I were to dump the values in the list node to an array before executing this code, and then writing the values from the array into the matrix, comma, then would that have some performance implications? I suspect that reading the values from the list node as I go actually harm caching. What do you think? So I'm thinking like maybe I could dump everything from the list node into an array first. Dumping the linked list into an array first would likely improve performance due to the better cache locality. Linked list traversal causes frequent cache misses. Nodes are often scattered in memory, so each next pointer dereference may require a slow trip to main memory. Arrays store elements contiguously, so reading sequentially benefits from spatial locality and hardware prefetching multiple elements are loaded into cache elements. array traversal can be 5 to 10 times faster than linked list traversal for large data sets due to cache effects. Extra space, upfront cost. List wants to fill matrix cache benefits outweigh the copy cost. Converting to an array first is a valid optimization. Okay, sure. Thinking is that maybe performing the dump, even though we'll have poor cache quality, will be beneficial during the writes to the matrix. The idea is that during the writes, cache isn't being tampered with. Obtain the list values. Thinking is correct. Okay. Initial dump might suffer. The subsequent traverse will be faster. It's not polluted by scattered pointer dereferences. Okay. All future accesses take fast cache, reducing memory latency. Pre-copying to an array is a valid optimization. Okay, try it. So, okay, let's give it a shot. Pre-processing dump. Let's do std vector int dump reserve by n dump.pushback. Okay. And so instead of using the linked list values, we're going to use dump of I, basically. Auto where equals dump dot begin. Increment the pointer. Dereference the pointer. Use an iterator here instead. Yeah, use a slightly different approach. Which may optimize the cache, which might help normalize make the performance more consistent. That's my thinking here. And faster. Hopefully it's not just more consistent, but it's actually faster and more consistent. Because what I'm seeing is that the performance is like kind of all over the place, which suggests that it has to do with like there's something weird going on with the caches, I guess. Let's try something like this. Use a pre-processing dump. So I'll have some initial like poor cache quality, but then the caching will be improved after that. Problem with this though is that it's like I'm doing an extra amount of work just to try to get the cache to improve, which might slow things down a bit. No, it's not much better, I think. No. No. I think that might work for very large arrays. But in this case, matrices are relatively small. I think doing the extra pass over the values list increases performance. It's a lot of 2 passes instead of 1. Yeah. Yeah, it doesn't seem to be much faster. Outweighs the cache benefits. An array can be 10 to 100 times faster than linked lists for sequential access due to cache effects. Pre-copying to an array improves performance despite the initial overhead. Array traversal is cache-friendly. Elements are contiguous, better spatial locality, efficient hardware prefetching, fetching. Yeah. Small data size. Extra pass adds fixed overhead. Node allocation patterns. Okay. Real-world data shows that for small structures, pointer chasing a linked list may not cause significant cache misses if nodes are allocated close together. Harms performance. Okay. Avoid premature optimization when the data is small. Okay. So there you go. Well, it's still relatively fast. It's not as fast as the previous solution. So that's interesting. Yeah, it's these things are too small for it to be worth doing that. Okay. Interesting. I had this misconception that leaving comments in your code slows it down, but now I leave meaningful comments in my code for my future self. Oh yeah. No, it does actually make the compiler slower. The compiler has to strip out the comments. It does strip out the comments. It doesn't make the code slower, but what does matter in large code bases is like code bloat and like the amount of lines of code you have. If it's a very large code base, when you compile, the compiler does actually take some time to go through all the lines of code. Compilers, what are, as an aside, what are typical compiler speeds? Then compilers are usually O cubed, where n is the number of tokens. I could be wrong about this, but I think it's like O(n) cubed. Meaning if you have a whole bunch of comments, it can actually slow down the compiler. But not really. I think it strips out the comments in like linear time, meaning it's really fast. So I don't think comments really meaningfully impact even the compiler speed. No, compiler speeds are not O of n cubed in the number of tokens. Run in linear and near linear time. Lexing, sequentially, parsing, many grammars, semantic analysis, code generation, optimizations can be higher with superlinear complexity. Oh. Oh, all right, never mind. Compilers are linear. Linear, near linear, log linear. All right. Register allocation. I think register allocation. I forgot what the register allocation algorithm is, but I think it's a coloring algorithm. It's NP hard, graph coloring, yeah. Linear scan allocation. Graph properties. SSA-based allocators, which I don't remember what SSA refers to. Linear scan register allocation for C++ compilation. LRA is a fast practical algorithm that approximates graph coloring but runs in O of n log time. Suitable for large programs, replace the older iterated register allocation framework to improve compilation speed and maintain good code quality. LRA works by tracking live intervals of variables, allocating registers in a single pass, spilling variables to memory when register pressure is high. Less optimal than full graph coloring, but offers a better speed quality trade-off for production use. What is the performance and expected time complexity of LRA? Is this one of the areas? Handwritten code. Handwritten assembly code. Optimized by so it's n log n or near linear time. N is the number of pseudo registers or instructions. It's designed for speed and integration with instruction selection, making it faster than older reload passes while maintaining good code quality. Avoids full graph coloring, instead using priority-based heuristics and iterative repair, which keeps compile time overhead low. Can handwritten assembly outperform compiler array? Yes, in specific cases, handwritten assembly can beat compiler register allocation type loops, predictable access patterns, register starved architectures, specialized workloads. From most code, they generate better equivalent register allocation. Global view of lifetime, sophisticated spill, reload heuristics integration with instruction scheduling. Handwritten assembly helps only when manual control of register usage avoids spills and performance critical sections. Does handwritten assembly ever really beat modern compiler generated assembly? Yes, handwritten assembly can beat modern compilers, but only in a specific performance